We went to put it all the way down. Yeah. 2, 3. Okay.
Alright, welcome to the afternoon session. We have 3 more talks today, and the first one will be by Andreas Kuper for what I presume will be about debris of cloning process.
Correct. So, I was working I'm currently based at Columbia University, which is in beautiful New York City. Stuck here, I put this up for stuck from water adventure is stuck. No. This is Central Park, and Columbia University is here in this northwest corner of the city park. So it's very beautiful. Come visit us. Sarah's also there. So the title of global clusters, why should we care? Since the 70s and this woman here, Vera Rubin, we know that spiral galaxies rotate faster than they should. If we just add up all the baryonic matter, looking at the rotation curves to determine that there must be a significant fraction of some dark matter or some modified gravity or whatever. Unfortunately, like for our own galaxy, we cannot easily produce a rotation curve. Several attempts have been published. This is from Heggie, recent paper, collecting H1 data, CO data, and masers all over the galactic disk, and trying to produce a rotation curve like we can so easily do for external galaxies. So if you try to model the galactic potential of our Milky Way and try to reproduce this rotation curve, you already see that you will need some form of dark component even within the quite limited data for the Milky Way, which is out to 10 kiloparsec. In this model here from Andreas Heggie, they infer that, of course, this is a vast extrapolation here, but within this radius of 100 kiloparsec, the dark component, if you assume it's an NFW profile, dark component, has to have like 1.7 times 10 to the 12 solar masses, so it's the dominant part in mass of the galaxy. So what else do we know about dark matter in our galaxy? All we do know comes from cosmological simulations of structure formation, like this one here, so we like tier 2 simulation from Demand from Zurich. Dark matter only simulation of a Milky Way sized dark matter halo. You see here, the top here is the scale, so this is 40 kiloparsecs, pretty much the inner halo of our galaxy. This is more or less what the dark matter distribution in our galaxy should look like. And if you measure the shape of such a halo, what you typically get is something triaxial. And what you also can see here is substructure, like very significant substructure orbiting within such a halo. But unfortunately, it's all dark, so we don't see it. So tidal debris can help us to see what we don't see, to measure the shape of this dark halo, and that's what we're trying on. We look at SDSS, very deep survey in the northern sky and also the southern sky. This is looking into the halo of the galaxy. And what you can see here, there's substructure, stellar substructure, very famous Sagittarius stream, which is a broad galaxy stream which wraps around the whole galaxy. And what you also see is the GD1 stream here is a very thin stream, most probably from a dissolved globular cluster, a remnant. It's also a more nearby orphan stream. And I'm going to talk mostly about this one here, the PAL5 string. It's like a big famous globular cluster string. But just this morning, there was the discovery announced by Carl Grillmeyer. He brings out every few weeks or so, he discovers new streams. Just in this data set, it's just So in principle, everywhere you look with a deep survey, a wide field survey, and you apply some matched color filter, you always find some sort of stream. So our halo is really full of streams. It's a bit hard to see here, but apparently this is the structure it claims to find. Very long, and another one running almost parallel to that. Not much information about that. Just this morning. So it's a very active field right now because all these surveys are coming up and there are more and more streams being discovered. But the first stream that was discovered was the Sagittarius stream. And this has been modeled excessively. The last and maybe best approach so far was from Law and David Law and ISIMA. This is their best fit model. So what they do is they construct a galaxy model, like a potential consisting of this and lodged in a halo, and then run an n-body model, a full n-body model of Sagittarius and look at the debris. This is the n-body model, and then they compare the debris to the observations. That's their best fit model. They modeled like 1,000 Sagittarii. And what they found is that best fit potential, this is like an illustration of the shape of the dark matter halo. I don't know why the colors, but apparently it's a very weird shape. So it's a triaxial halo like we expect, but it's like a disk, dark matter disk, but it's tilted 90 degrees to our baryonic galactic disk. It's a very weird configuration. So if you look at the literature, there have been many other people trying to model the Sagittarius stream, and they found all kinds of, they found prolate halos, they found oblate halos, they found spherical halos. Recently there was Cambridge group modeling Sagittarius found spherical halo, which is very low mass. They claim to find that the missing satellite problem is not a problem because we just have a very low mass halo. It's a very controversial stream because it's very hot and broad, and observations are with large error bars. So that's why we want to go to globular cluster streams, because they are much colder, dynamically colder. They are very thin, and consequently you can measure distance easily because it's just one population, because it's a globular cluster. So, and the two most promising streams are Palomar 5 and NGC 5466. This is from a recent paper from Lux. This is illustrating the galactic disk here, the sun is here, the galactic center is here, just showing where these streams are. So this is the Sagittarius stream here, and this is Palomar 5, and this is NGC 5466, a very long structure. This is from the side, like this here, Palomar 5, NGC 5466, and Sagittarius. You see, Sagittarius is very long, very long fixed structure. So the question is how to model that. Yes.
People underestimate the orbit of it seems extremely high up. It's very helpful in mind in your
That's what like very basic modeling suggests. And so far there's no kinematic data, no radial velocity data. But in the project I was suggesting here, we now have some radial velocity data, so we can try to look at possible orbits, whether it's radial orbits. So how to model streams? As I said, like Sagittarius was modeled with n-body simulations. There are different techniques how you can approach this problem. Direct n-body simulations, of course, would be the nicest approach. Just set up a cluster or a dwarf galaxy and you let it dissolve still consistently in some trial potential and look at the debris and compare it to observations and then say the model is still a best. But it's super slow. Simulations take at least a day, or depending on what kind of object you want to model, maybe a month or so. The simplest thing you can do is called orbit fitting. What you just do is you look at the debris and you try to find an orbit, just one line going through the debris. But this has been shown that it's a very low accuracy, it's very degenerate, and also produces biases, and we don't want biases. So what I'm suggesting is something in between here. It's the restricted free-body problem. So what we do is we assume that once stars have left the clusters, they don't interact among each other anymore. So we can treat the problem of cluster, debris star, and galaxy as a restricted free-body problem. It's called a Strickland problem, and I will show you how this goes in detail. So from Douglas' lecture, we've seen that very schematic what happens in a cluster. This is the cluster, and we're in a moving frame. We have these exponential surfaces here forming two holes through which stars can escape from the cluster into the tidal tails. And every star escapes through the Lagrange point, which is closer to the galactic center, it speeds ahead, and the one and the two, they stay behind and form the trading tail. So let me show you how this goes. And let's imagine you have a galaxy and there's a cluster going on a circular orbit. Now we'll show you an n-body simulation, a full n-body simulation of cluster. Oh, no. Let's start now. Yeah, so cluster is very compact in the beginning, and we just go with the cluster around the galaxy, and you see slowly that on the right, this should be the leading tail, here this is the trading tail. And the stars, they funnel into the leading tail. And when we go around once, then the tails grow. You can also see here is that they form a substructure, which is very interesting, you can also use. I'm not going to talk about this here. And so it goes. So the longer the cluster revolves around the galaxy, the longer the tails get.
Where does it come from? Is it self-gravity?
No, this is epicyclic motion. So I can show you later a few slides how this goes. It's in principle, the motions along the stream are not linear lines here, but they are stars escape in epicycles around this, because there are small differences in angular momentum to the cluster. So there's always a relative motion between the cluster and the tail. And this is like a standing density wave in the tails. Okay. So there's a lot of information here. We're trying to make use of that. So there's a lot of information in the location of the clumps, because it's proportional to the offset from the cluster to the Lagrange points where the stars escape. So in this distance here, there's a lot of information on the cluster and also on the gravitational potential, on the strength of the potential. And as you will see now, for an eccentric orbit, we look at the same thing but on an eccentric orbit. It's the same game, stars escape, but then on top of that motion, out of the cluster, there's the motion of the whole system around the galaxy. So it goes into, so now it's going into pericenter, the thing is speeding up, it's stretched the whole system, and then going into apocenter, the whole system gets compressed, and it's getting stretched, getting compressed and stretched. And what you can see is these overdensities form, and they also form these funky shapes here. Which is very, very stable. So there's not just information. So in this distance from these overdensities from the cluster, there's information about the mass of the cluster, the strength of the gravitational field, and also about the orbital phase of the cluster of the galaxy. So, but as I said, these simulations take maybe a day, maybe a week. It's way too long to scan a huge parameter space of potential models.
So are the stars coming out of the cluster at a steady rate, or do you evaporate more stars when it's at pericenter?
That's a good question. So what I find, it depends, okay, crucially depends on how you define what's bound to the cluster and what not. If you define stars to be bound to the cluster when they're inside the instantaneous Jacobi radius, what I always see in my simulation is that the mass loss rate is just constant.
Oh.
Yeah. Then maybe in pericenter, the instantaneous Jacobi radius may be a bit smaller. And stars beyond this radius may be unbound for a time. But then they get recaptured as the star cluster, as the whole group moves into apocenter and the Jacobi radius grows. They can be recaptured. And on average, you get a very linear mass loss rate.
Just while we're working on
Yeah.
some questions. For the tails, where you see this pumping from epicyclic motion, does that suggest that there's a phase dependence on the stars as they're lost? Meaning phase of the epicycle.
How do you mean that?
So, I mean, if they're pumping, so in my mind anyway,
Mhm.
then there maybe would be some sort of relationship between the stars that came out, that were lost as they move around and you see this pumping from. Because they're in nearly the same epicyclic phase. Once they enter the galactic dimension versus the
Yeah, as I will show later, so these tracks of the stars within the tails are very complicated on eccentric orbit. They, especially if you have these freaky features here, they go like this. So it gets overdense in this position where two tracks overlap. So and these the stars in one overdense, they can be from very different like escape times. So there can be stars in here, for example, that were lost 2 orbits ago and 1 orbit ago.
Okay.
Yeah. So not really. It's hard to say. Okay, so coming back to the straight line modeling, very simplified modeling that. What's a straight line? A straight line just imagine you have some flow, some background fluid or a gas and so on, and you insert some object and you release test particles from a given point of this object, like for example, imagine this is the cluster, it's moving through the galaxy, and this is a branch point and we are just releasing test particles, and then we follow the airplane and these particles, how they evolve over time. And if we look at that picture, we compare it to our observations of Alpha 5, and then we assess if it's a good model or not. And it turns out that with this very simplified description, you can reduce the shape of these streams. So this is now from the circular orbit model that I show you. The clusters here, the black dots are stars from the simulation, from the full n-body simulation. And the red ones here are like points from the streak line modeling. As you can see, you get this pattern here reproduces very precisely. And also for the eccentric orbit, getting a bit more convincing here, you produce all these spiky features to very high detail. And the big difference is that producing a streak line model may take like a second, whereas full n-body simulation takes a day.
So for the streak line, you're assuming 0 velocity when it escapes?
Yeah, that's a tricky question. So we played around with this. Douglas and I, we published a paper on that. So you have different choices you can make, right? And we compared different choices. What we found is if you give the particles exactly the angular velocity of the cluster, then you end up with these streak lines I've just shown. If you give them the same space velocity, for example, the loops get too long, or you make them slower, and they get too short. So it seems like that on average, stars escaping from the cluster have the same angular velocity as the cluster. But of course, there's like in a real cluster, there would be a lot of spread around this.
Do you understand why?
Hmm?
Do you understand why?
What?
Why is it that the streak is
No, it's a good question. I don't know. Okay, coming to Power 5. Now I want to apply this. Briefly, let me present Power 5. This is Power 5, beautiful cluster. You can barely see it. Has a central density here, 1 star per parsec squared, so it's really very, very sparse. Therefore, ideal for making n-body simulation of that thing. Has a absolute magnitude of -5.1, so it's about 10,000 solar masses. Very extended, as I said, 20 to 30 which means parsec actually. It's 23 kiloparsecs from the sun and like 19 kiloparsecs from the galactic center, and it's high above the galactic disk. So in SDSS in the northern footprint, it's on the southern border of the footprint, but it's well above the bulge. And if we look at the mass function, for example, there's HSD data on the mass function in clusters, and it's very depleted in Loma stars. And these Loma stars are, this is maybe which hints where they are. So this is the surface brightness profile of the cluster you see here. That's the part as you would expect it to be. You would expect surface brightness profile of the cluster to drop like that. Typical pink profile. But what you see is it levels off, and then you have this very shallow slope outside the tidal radius, which is more or less here. I've shown the other surface brightness profile for 1851, the other project I was advertising. 1851 has an even shallower profile here, so it's almost constant. And if you look at Palma 5, no matter how you model the cluster, you always get some orbit with an eccentricity of 4.5 or so. Orbit explicit 4.5. So most likely NGC 1851 is on a very much more eccentric orbit, and it comes to its upper center. That gives you this shallow slope. So where does this come from? This comes from the debris of the cluster. So here is the cluster, and this is early data from SDSS, like the first, it was before the first data release actually. Wood Kit et al. They looked into this, and they found this first part of the tidal stream, like the stars floating out into the tidal. It's very beautiful. Like in the last data release of SDSS, you can trace the cluster, the tails out to 22 degrees on the sky. Very long structure. It's like 10 kiloparsecs in total. So what else do we have in data? So there's also some kinematic data. So the same team went to CAC and took some radio velocities here of stars where I thought there might be members of the tail. And the red ones, red dots are actually kind of confirmed cluster members. What you get is some sort of radio velocity gradient. So when we model the cluster and the debris, we also want to reproduce this velocity, the radio velocity gradient along like the longitude there. Woodkick and in the same paper, they also tried that to model that with orbit fitting, as I said. And as you can see here, so they have 3 lines just going through all the data points there are. It looks like one line. It's how they generated this. And you get different gradients here in radio velocity. And what they inferred is that the halo must be very, very low mass so that you get a rotation velocity of 150 kilometers per second to match this radio velocity gradient. But people have shown that just fitting in orbit is biased. So we need to model it more properly. That's what we're doing. So let me briefly explain the method, how to produce such a streak line. So assume you have your position of Palma 5, you assume some distance, you have a radial velocity, you assume some proper motions. What you then do in a trial potential, you integrate it backwards for a given time, and then you start the simulation forward again, and while going forward, you release these test particles, and you integrate everything forward in time until the present day, and then you get a distribution of test particles, which you then can compare to your observations. This is a very schematic movie, but I like it. It's from Anna Vanazza from Yale. running the paper on this right now. So assume these are observations, the black dots, and then this color line here are the test particles. As you can see here, the color coding here is it's like when the test particles have left the cluster. So you see here they are all overlapping the colors.
Can you explain how the streamline models are different from just doing orbit integrations with test particles that are released from the cluster's potential?
Sorry, I don't hear you acoustically.
Sorry, can you explain how the streamline models are different from just doing orbit integrations of test particles that are released from the cluster potential and then are just moving in the host potential? Or is that?
You mean what people also do is like setting up a ball of stars and evolve it forward without self-gravity of the ball of stars, right? Mm-hmm. What you don't get in this is because you don't have self-gravity, you don't get an offset of the test particles from the cluster. Mm-hmm. So you would just spread the debris along the orbit of this ball of stars.
Right.
So, but what you need is this offset. Just imagine, make the cluster much more massive, like Sagittarius massive. Yeah. Then the debris would have to have a huge offset from this initial group of stars, and you would not reproduce that.
Yeah.
So that's the difference here. So then you have a streamline model here. You have a streak line, and you have to compare it somewhat to the data. You need some likelihood function to spend more time to figure out how to compare its best. I'll talk about this in detail if you'd like. So Sarah has been working in the last year on this, trying to assess what we have for Plummet is the position on the sky, right? You can measure it very accurately. We have a distance, which you can measure more or less accurately. We have a radial velocity, which is also measured to a very high certainty. But what we don't have is the proper motion. And what we of course don't know is the dark matter halo. So what we assume here is we have a spherical dark matter halo potential, and we just vary the proper motion and see for each pair of proper motion components, what do we get? What does the model look like, and what does our likelihood function return? So what you see is for two proper motion components, the log likelihood value. So dark blue is very good, and white would be completely wrong. And as you can see, we can rule out like large fractions of proper motion components, which you could also do by eye, because if the cluster, if the tails lie like this, then of course it's wrong. But what we find is like the best model here, if we run an n-body model with these proper motion components, we get a variable match to the SDSS data. It's just on top of that. If we then take, as an example, this potential which was found for the Sagittarius stream, very simple exercise, just take the same triaxial potential and try to find the best fitting model in that potential. You see it has a very different proper motion here, and then if you run an n-body model for that, you kind of get the shape right, but what you see here in this blow-up, very nice blow-up by the way, you see it's totally off. So the stream is not really curved like it has to be, like here. And it has a much lower likelihood value. Like the likelihood value, the log likelihood value is like 20 magnitudes lower as for the spherical halo. But we have more information, right? We have also the kinematic data. We look at that and it's much more clear. Here the radial velocity gradient just matches spot on, whereas in triaxial potential on this side, it's completely off. So we have to make an triaxial potential like the one suggested by Majesty. You have to make the cluster very, very fast so that it's closer to pericenter, that the whole system gets stretched and it just looks very straight. So you can kind of just rule out this triaxial and halo configuration for the one that Majesty suggested. But we can go further. We can put this machinery into MCMC from Daniel Forman, Mackie, and NYU. and increase the parameters. So we can just leave all parameters free. So 11 now. For example, like the halo shape, you can leave this completely free, and also like the geometry of the problem, like what's the distance to the cluster, what's the distance of the sun to the electric center. All these are free parameters. And what we get from that is now an attempt of comparing my results to other results. These are from different tracers. For example, Neden used globular clusters in a way to infer the mass of the galaxy. You get these huge degeneracies here between mass within a given radius and halo concentration, for example, halo. This is kind of the uncertainty we have to deal with. So it's an uncertainty, for example, for this black contour line. It's an uncertainty of a factor of 2. So if I plot my results into that, they're in very good agreement with all the other methods and have smaller error contours. So what this means is that within a radius which contains, okay, what is N340? N340 is the mass within a radius at which the density of the dark matter halo drops to 340 times the critical density. How small it is, yeah. Which is more or less 100 kiloparsec. So the mass inside 100 kiloparsec is about 1.2, 1.3 times 10 to the 12 solar masses. For the flattening, might not slight. For the flattening, we get something close to spherical, maybe slightly oblate, and that's it. So not triangular at all. And that I conclude. Thank you very much.
Thank you very much, Andreas. Any questions that you touched upon yet?
Are the two streams symmetric?
Say again?
Are the two streams symmetric?
Symmetric?
Yeah.
No, not at all. That's very interesting.
Because I think it's not symmetric. Maybe it will affect the trajectory of the cluster.
Yeah. So the trailing tail of polymer 5 is much more dense than the leading tail, and what we think the reason for that is that the cluster is right now close to its apocenter, and it might have just passed its apocenter. And the densest part is the part which is still in apocenter. So what we see is there's the apocenter and the cluster is already moving out of apocenter. So that's why you always expect this asymmetry.
Yeah, so I'm asking whether you have to consider the effects on the trajectory, because we have different amount mass on two streams that will affect the trajectory of the star cluster.
Oh, no. Mass-wise, it's the same. It's just that the leading debris is more stretched out because it's already falling into pericenter, whereas the trailing debris is being compressed. So, but no, the mass loss is symmetric. Yeah. The thing is, we don't see the polymer 5 is right at the edge of the footprint of SDSS. So from the leading tail, you only see 2 degrees or so, whereas from the trailing tail, you see 20 degrees. But that's up to it.
Both the giant stream and polymer 5, can you minimize them together to get the better results?
Yeah, of course, that's where it's all going.
This was just for polymer 5, I'm sure.
Yes. And here, with the student, I wanted to try to also model NTC 466, and then the next logical step would, of course, be to combine. You can apply the same for Sagittarius. The Cambridge group has applied exactly the same methodology. So.
Somewhat related to that. Oh, sorry. I'm assuming you're not sensitive to anything that happens beyond the apocenter of the orbit, right?
No, not really. I mean, what we do is you assume some parameterization for the halo.
Yeah.
So what you can say is, if our dark matter halo has an FW shape, then of course you're sensitive to scale radius and scale mass of the FW scale. And to explain the Palma 5 result, you need a certain scale radius, which actually lies outside the upper center.
Yes. I was quite surprised you're constrained on C, which is mainly scale radius and the outer radius, isn't it? And that's very small. Your error bar is pretty small there.
Right. Because you have to make this, I mean, once you fix the parameterization, then, I mean, no matter what constraint you get, 4.5, we don't know what the dark matter profile is beyond this radius, but if it's NFW, then this is the error bar you get.
But isn't C telling you more about what happens beyond the scale radius? Was it also parameters or something like linear?
It also has an effect on like inside the scale radius.
Yeah.
Did you use your streamline models to predict the orbits of the broader cluster, or predict the proper models? If you, I used to assume a potential instead of solving for one, but.
Yeah, of course. I mean, you saw that in plot from Sarah's paper. Like field prediction, if we say, if someone else claims that the NFW halo is circle, then this would be the proper motion we should observe.
Okay.
Well, most likely. Of course, we could also put an arrow on that because it's basic.
Okay, a number of questions. Let's thank Andreas one more time. And we move to Dr. Heggie, who's going to tell us what we do not know about double cluster dynamics. Sweet, because we did that
Okay, so it may sound, really became very, very tired of my voice by now, so this is the fourth day in succession I've been speaking. And it may seem extremely arrogant to try and explain what we don't know about star cluster dynamics in half an hour and 15 slides. But in fact, this talk is a kind of extended sales pitch for the 6 projects which Annalisa, Vary and I proposed for the students. And I'm presenting it now just to give you an impression of the sort of areas of star cluster dynamics which are not only unknown but also, I think, approachable and penetrable in the mixed environment. And as I mentioned the other day on Monday, the 6 projects divided up into 2 main themes, tidal field and thermal rotation. I'm going to begin not quite with the first of the projects which we mentioned, but it's appropriate to start with this one because it does show you what I think was, well, except for the truncation of star clusters, the first ultimate observational evidence that the tidal field was somehow affecting the stars inside the globular star cluster. This was some observations of the kinematics in M15 from Gordon Drucke and his colleagues, 1998. So this is the velocity dispersion. The line of sight velocity dispersion is a function of projected distance from the center of the cluster. And it falls off, but it doesn't keep falling off. The tidal radius, by the way, is around about 24 arc minutes, around about here. And what one sees is that the velocity dispersion appears to drop off fine to begin with, and then it stalls at a value of a few kilometers per second. And this kind of phenomenon has been observed in a number of other star clusters since then. And a certain amount of nonsense has been written about this kind of data, because if one believes that star clusters follow things like King models, then there should be more or less a Keplerian drop-off in the velocity dispersion right towards the tidal boundary. And here the velocity dispersion isn't dropping in the expected way. And some people have even been tempted to say that there's some kind of non-Newtonian dynamics exhibited by these star clusters towards the outside. Now, the truth of the matter is that King models and so on aren't very good at doing the effects of tides inside the star cluster. N-body models are, and this diagram from one of the many, I think, sort of mosaic of diagrams from Andreas, showing you the velocity dispersion as a function of projected radius. This time it's logarithmic, so it's very compressed at large distances. And the velocity dispersion, he's divided the stars up into three groups. The blue thing is what you would get if you could somehow mysteriously only include those stars which are inside the tidal radius of the star cluster, and its energy is below the energy at the Lagrange points, which have been discussed several times now. And then one does get a very beautiful fall off of the velocity dispersion towards zero, towards the tidal radius. But if you include stars which are inside the tidal radius, certainly in projection, and you couldn't distinguish these from sort of bound cluster members observationally, then one finds that the velocity dispersion doesn't keep falling off. It actually does saturate. It does move to saturate for a great distance here. But remember, this is a logarithmic radius axis here, unlike this one. And in fact, there's a significant range of radii where the velocity dispersion is almost constant. And then beyond there, one gets very, very few stars, a lot of noise, but not much change in the velocity dispersion. But these stars are genuinely outside the tidal radius. So what's happening here is that there are stars which are inside the star cluster, actually inside, even 3 dimensions inside the tidal radius, and this energy is sufficient to allow them to escape if they don't escape. And these are the things which are called potential escapers, and they are largely responsible for this elevation of the velocity dispersion profile, and the fact that it doesn't drop off to zero. Now, what kind of orbits would these stars move on? Now, here's a picture from Enon, and I've quoted many times. It's not quite the star cluster problem that I was talking about. It's actually a build problem. But there are still Lagrange points at plus 0.7 and minus 0.7 in this diagram. And also he's drawn here a family of periodic orbits in the Hill problem. And it turns out that this number, which labels them here, corresponds to minus their energy. And if the energy is less than around about 4.3, these are stars which are above the energy of escape from the star cluster. But you can see that there's a finite range of the orbits in this family which are above the energy of escape, but inside the Lagrange radii. So these are good examples of potential escapers, stars which would remain there forever, because these are stable periodic orbits actually, if the cluster potential itself did not change. So the project, Project C, is meant to try and explore the effects of orbits like this. And the idea is simply to repeat the simulations like those which Andreas made, or just ask him, buy him a beer and ask him nicely for the data.
Never.
All right. It doesn't drink beer, okay. And then reanalyze the kinematics of the stars inside the tidal radius, not simply in terms of the velocity dispersion, but also in terms of the signal of rotation and also the signal of anisotropy, which I think was something which he did properly examine. Then to understand the results in terms of the orbit structure of potential escapers, for example, N-O's family F, and the quasi-periodic orbits around that family, and then if time permits, extend to elliptic galactic orbits. Many of the projects on offer here are concerned with elliptic orbits as well. So that's one perfectly doable project. Here's a project which is at the opposite end of doability. But one which has been the apple of my eye for an awful long time. It's concerned with trying to construct a cluster model which does actually include potential escapers, and there's no model in the universe, as far as I know, that does this yet. Now, this wouldn't matter if the number of potential escapers was quite small. The n-body simulation suggested that it had an observable effect. And in fact, what's been done here from some old simulations by Holger Baumgart is to plot the average number or the average fraction of potential escapers in an n-body model as a function of n. Now, the n-body models won't get up to the values of n appropriate to star clusters, but the dependence on n is very weak. It's actually even more weak than n to the minus 1/4. And so by a simple extrapolation of this, one can guess that there's somewhere between 5 and 10% of the stars inside the star clusters that we observe, which are potential escapers and have energies above the energy of escape. So, if you devise a model which doesn't allow potential escapers, your model is excluding 10% of the stars already, and nobody understands, I don't think, what effect that has on the inferences that one makes from that model fitting. And I think I mentioned already that these potential escapers, through the principle, explain high velocity stars, which are sometimes observed in velocity maps of a star cluster. Here's one from Lutzendoff's recent paper, I forget which cluster this is. This is one of these velocity maps in the center of the star cluster. And these bright blue pixels here correspond to high velocity stars, which are thought to be cluster members, and they're in decent position in the cluster color magnitude diagram, but obviously moving at several times the typical velocity dispersion, and in some cases above the escape energy. There's also another one here, but its blue light, as it were, is swamped by a whole lot of contaminant with more normal velocity. So the idea of this problem is to try and construct for the first time a model of a star cluster which includes potential escapers, and you might become famous if you do this successfully. Ivan King's 1966 paper inevitably fits King models. It's got something like 1,800 citations since 1966. And for all the students here, this is the kind of thing to aim for. Right? The paper has got 1,600 citations. I usually talk about this in lectures at summer schools. And the one thing I have to change in my lectures is how many citations King's paper has got, because it keeps increasing by about 100 every year. Okay, so how would one do this? I'm not quite sure. This is why this is such a tricky problem, actually. I mean, I would start with some well-known potential. I'm not even sure if I'd start with King. I might start with the point mass potential or an isotron potential. Find out where these periodic orbits are, and in almost family F, And this is a diagram of the potential well that just the lead pumps around the Lagrange points here. And it's kind of at 90 degrees because in the old days they used to do things in sort of a curious orientation. But this line here marks the intersection of the family F orbit of the gain energy, because it's energy up here, and with the x-axis. So this is what's called a characteristic curve which delineates this family of periodic orbits. Even more important is numerically determine the range of intersections where you get orbits which oscillate around this periodic orbit, rather like x-cycles around the orbit. So what one wants to do is to try and understand the phase space distribution of these orbits in the vicinity of family F, and then try and invent a plausible distribution function which populates those orbits. But now that's all in the context of a potential which you've assumed. This is no longer a self-consistent model at this point. So the next step would be to compute the density of that extra component using some kind of Poisson solver, recompute the location of the periodic orbit and its bound, its associated companions, and then keep iterating that process to produce a model with potential escapers. Well, that's a hard job, and somewhere in between is a problem on tidal effects. I better get a move on here, actually, which I discussed with several of the students who are interested in it. But it's basically the problem of trying to extend our understanding of escape from star clusters from the circular orbit case, in which one has nice equipotentials like this, to the case of an of a star cluster going on an oval galactic orbit. And I'm going to have to cut this one short, although it's my favorite project in a sense, actually. And there are several complications which arise when the cluster is moving on an elliptic orbit. First of all, one doesn't have a conserved energy, and therefore the existence of these equipotentials is of no physical significance. They don't actually constrain the positions of the particles anymore. The second thing is that this is a time-dependent potential, what's associated with the first thing, and therefore the positions of these equipotentials is also oscillating in and out. The third thing is there's no such thing as a Lagrange point. Well, it depends how one defines the Lagrange point, and that becomes a bit critical. You could define the Lagrange point as the critical point of these equipotentials, but then, the fact that in the circular case, this is an equilibrium that you're equating with motion goes out the window if this critical point is moving in and out as it would do in a time-dependent potential. And my best guess is that the thing which replaces the Lagrange points is a periodic orbit with the motion of the cluster around the galaxy. Well, why is an understanding of that kind of thing important? Well, it turned out that the flux of escapers past the Lagrange points here, which was something one could compute fairly readily, turned out to be critical for understanding why it is that the lifetime of a star cluster on a circular orbit is not quite proportional to the relaxation time like had been thought for decades and decades. It was Holbert Baumgart who investigated that issue, and as I say, what I'd like to do is to try and extend that understanding from the circular case, where the understanding does exist even if it's a little bit shaky in places, to the eccentric orbit case, because Mark had this lovely diagram in which he showed that the lifetime of a star cluster for fixed something, I can't remember exactly what it was, depends linearly on the eccentricity of the orbit. And I don't think we understand that at all. On the other hand, I think with this program or this project, we could understand that these parts should be proportional to the eccentricity for smallness. That would be my best bet for the hopeful outcome of this project. Okay, I better get on to Annalisa's favorite topics, which is basically rotating star clusters. And she again has three projects. These are two examples of the fact that globular star clusters do rotate. Here's one of these velocity maps again, there's more red on this side, more blue on this side, meaning one side's approaching on average, another one's receding an average, and you have this paper from Kaczarov et al., one of the authors is sitting around the audience, I think, actually, and again illustrates the rotation curve of this globular cluster. Now, the point of this project is to try and understand the interaction between rotation and mass segregation. Totally unexplored area as far as I know. And so this project has two pieces. One is simply to try and investigate this problem with n-body simulations. You start with moderate differential rotation and the mass spectrum. Just to investigate what happens, try and find out what happens to the rotation profile, try and understand the evolution of the rotation profile in terms of transport of angular momentum. While your n-body simulations are running, as long as you don't have to spend all day babysitting them, you can have a go at investigating how to construct multi-mass generalizations of the rotating models which Annalisa's the world expert in. So there are two parts of that project. This part will keep you going for in week 2, and then weeks 3 and 4, while you're waiting for the results to come in, you do this piece. And then she would like to try and develop another extension of her rotating models, which is to include a central point mass singularity, in other words, an intermediate mass black hole. Because I think explicitly rotation is assumed to be absent in the observational programs that try and infer the existence of intermediate mass black holes, and it would be very helpful to have a suite of models, rotating models, which have both rotation and a black hole. And there are possible extensions of the application of these models to nuclear star clusters, of which this is a lost in map. It's a gas map, actually, of the Milky Way nuclear star cluster. And there are various things which Annalisa would like to understand on the basis of these models. I've got to pass on from here, but she's interested in the short time scale evolution of instabilities in the rotating model. I'll come to that again in just a moment. And also the long time scale evolution of the models which are dynamically stable. So, last, this is a pure curiosity-driven project, which is to go into the domain of rapidly rotating stellar systems. And I will go back just to show you this diagram here. This is what she means by a rapidly rotating stellar system. It turns out that there are dynamically stable models which have this kind of toroidal distribution of density. This is a meridional plot of contours, Heggie contours, and simply as a matter of curiosity, not quite simply as a matter of curiosity, but certainly that's the main motivation to find out what happens to this toroidal structure in the short and the long term using n-body simulations. And I say it's not entirely a curiosity-driven matter, but there are some cases of observed young massive star clusters like R136, in which the rotation speed here, V, is quite large compared with the velocity dispersion, and even larger than you saw here. Finally, in terms of the applications of this project, she's interested in trying to see if there's any physical way of making sense of observations like this. This is an object in the Large Magellanic Cloud by reputable observers, in which if you do surface brightness profile, you'll find that there's a dip, in other words, a kind of hole down in the middle. And you can almost see this here, that there's a kind of ring-like structure of the bright objects